turn this on. Okay, good afternoon everyone. Good afternoon. For today, I'm going to solve two problems on Bode magnitude plots. Okay. So plan going forward, I'll be spending most of today on solving example problems. Wednesday, I'm going to take a circuit, solve it from scratch, draw the Bode plots, and then we will look at the process of linearization of nonlinear systems. And then the last three lectures, we will be talking about fluid systems. Okay? All right, so here is an example. I am going to go at a fast clip today. So if you do have questions which require an elaborate explanation, we can talk after the lecture. Okay? So first problem. You're given the following system. We have to draw the Bode magnitude plot. As I said, we are not interested in the phase plot because as a mechanical engineer, it holds very little glamour for us. But the magnitude plot tells a lot about the response of the system to ranges of excitation frequency. Okay? So, draw the Bode magnitude plot. And as usual, I like to follow certain steps. So given any kind of a system of the following form, which is a second order system in this case, I would first like to compare it with a standard form and then obtain the system parameters. Okay, so first step, obtain omega n and zeta. Okay, so the standard form, x double dot 2 zeta omega n x dot omega n square x is equal to g of t. This is the standard form. You compare what is given with the standard form. In some situations, you will have to divide through by the factor that, or the coefficient of x double dot. In this case, I don't need to do it, okay, because the coefficient is 1. So if I compare, omega n square is 1000. So that omega n is square root 1000, so many radians per second, not really interested in the numbers. And then 2 zeta omega n is 110. I know omega n is square root of 1000. So solve for zeta. Zeta gives me 1.73. Which is greater than 1, so this makes it an overdamped system. Okay? So that's the first step. And then what we do next is the following. So you see in this particular problem we have numerator dynamics, right? You have certain derivative terms existing on the right hand side. So those are called the numerator dynamics. What we will say is this. If there were no numerator dynamics, and if the value of zeta was 1.73, would I see any physical peaks in the magnitude plot? Once again, if there were no numerator dynamics, if you club all these terms and call them as some g of t, okay, And given that the value of zeta is 1.73, the question that I would ask myself is, will there be any physical peak for the magnitude of the system, right, in the frequency response and the frequency domain? And obviously, we know that that is not the case, because a physical peak is present in the absence of numerator dynamics. Physical peak is present for the magnitude of the frequency response function is present only for zeta within this particular range. Okay, so we know this is whatever I said in words written here. So obviously for zeta of 1.73 there is no physical peak present in the absence of numerator dynamics, so move on. So for our case, no physical peak, which means there is no resonant frequency and so on. Okay, so no resonant frequency. Does this make sense to everybody? Okay. Alright, so the next step is I take the Laplace transform on both sides of the given ODE, write the transfer function of the system. Okay. So Laplace transform on both sides. So S square 110S x of s, right? If I take the Laplace transform of x double dot is s square x of s, 110 times s times x of s, 1000 times x of s. X of s is a common factor, take that out. Right hand side, please be careful, there is an f dot present. So this is going to be 100. 100 is a common factor, so I'm just taking it out there. So this is going to be s plus 1 f of s. Okay, so take Laplace on both sides. System transfer function. Output Laplace transform divided by the Laplace transform of the input. So this is x of s by f of s. Okay. So I have t of s is x of s by f of s, and I already have an inkling of what the characteristic roots are going to be. They're going to be real and distinct, right? Because I have an overdamped system. If you have an overdamped system, which means if zeta is greater than 1, you're going to have real and distinct roots. If you have zeta is equal to 1, that's a critically damped system, you're going to have real and repeated roots. If your zeta is less than 1, you're going to have complex conjugate roots. Right? We've gone through this many times. So x of s by f of s is 100 times s plus 1 s square 1. This is obviously not in the form that you use to draw the Bode plots, because I'm going to tell you what that form is. So first of all, roots of the characteristic polynomial. What's a characteristic polynomial? It's the polynomial in the denominator, right? So s square 110s, basic stuff. Roots of the quadratic, you will end up getting this to be minus 10 and minus 1. S1 minus 10 . They are real and distinct, which completely aligns with our idea of zeta being greater than 1. Okay? Alright, so once you have figured out the roots, go back to the transfer function, rewrite it in the following form. So T of S is 100. S plus 1. First root, what's the root S1 called? What's it called in our jargon? What are S1 and S2 called in our typical jargon for ME3260? Yes? Poles of the system, absolutely. Okay, what's S is equal to minus 1 called? That's called the zero of the system, right? When S is equal to minus 1, the whole system transfer function becomes 0. When S is equal to one of the poles, the system transfer function becomes infinite. Okay? Alright, so I write it in the form that we've been seeing it in the past. But this is not the standard form you want your transfer function in when you draw the Bode plot. Okay? For the Bode plot, if you have real and distinct roots, or if you have real and repeated roots, real and repeated is nothing but a special case of real and distinct, right? There is nothing different about it. So if you have these two situations, and mind you, not the complex conjugate pair, I haven't spoken about that, my next example is for that. The standard form is some constant term, okay, so some capital C, and then S by omega Z1 plus 1, okay, which is nothing but your zero of the system. I just write it as a frequency because you're now doing analysis in a frequency domain, right? And then divided by S omega P1 plus 1, omega P2 plus 1. If you have a third order system, you will have 3 real and distinct roots. You have a fourth order and so on. We typically stop at the second order analysis in this course. So this is the standard form. You always want to write your transfer function in this particular form if you are drawing the Bode magnitude flows. Okay? And I do that on our transfer function here. Before doing so, this capital C is called the DC gain of the system. This is essentially the value of the transfer function when S is equal to 0. Okay? When S is equal to 0, you will just see that the transfer function is equal to C, which is the DC gain. I am not going to go into the details of this because you're going to see this again in control systems on a much more elaborate manner. So I write our transfer function in the following form. So T of S, 100, can't do much about that. The first 0 is 1, so I just write it as I took 1 as the common factor. Okay, so look at this. What I did was from the numerator I took this 1 outside, common sense, and I divided everything by whatever I took outside. I do the same thing in the denominator as well. The first one, I take the factor of 10 out. Okay, so that's 10 times S by 10 plus 1. And in the second one, I take the factor of 100 out. S by 100 plus 1. And then I clean up my act. Okay, I take all the constants, club them together. There's a factor of 100, a factor of 100. The numerator and the denominator cancel them off. Sometimes you get lucky. Then this factor of 10, a factor of 1, I club them together and write it in the numerator, or write it separately. So this is 1 by 10, which is what I'm left with after all the constants are taken care of, S by 1 plus 1, S by 10 plus 1, S by 100 plus 1. This is the proper form if you are drawing Bode plots. Okay? Why we are doing this is because of convenience. That's all it is. There is no special secret sauce here. Once you bring your transfer function to the following form, which is for a real and distinct case or a real and repeated, it's a special case of that, you calculate the frequency response function. So FRF is P of j omega 1 by 10. Wherever I see an S, I substitute j omega, so j omega by 1 plus 1 divided by j omega by 10 plus 1, j omega by 100 plus 1. This is my frequency response function. We are drawing the Bode magnitude plots, which means that I need to take the magnitude of the frequency response function. I'm going to do it in two locations. I'm going to do one here. I have to rewrite it again, so you don't need to write it twice. So magnitude of T of j omega is nothing but the magnitude of the numerator divided by the magnitude of the denominator, right? Numerator 1 by 10, leave it as it is. Then magnitude of the first term is the square root of the sum of the squares of the real and the imaginary part. So that's 1 square, omega square by 1 square, square root, right? And then divided by the rest of this garbage is 1 square, omega square by 10 square, square root, right? So that's the magnitude of the frequency response function. I'm going to write it once again because I'm going to draw the Bode plots of this. Alright, so magnitude of T of j omega 1 by 10 omega square by 1 square whole square by 1 by 2, I'm sorry, this is a 1 by 2. Okay, so these are the magnitudes. And if you want, you can also write it in the following manner. This is equivalent to the DC gain, the constant C, 1 by omega square plus omega z1 square. One by 2. Omega p1 square. 1 by 2. Compare omega z1 is 1, is 10, all in. and I'm going to work with the general form. Okay, I'm not going to work with the numbers. Okay, so once you have this, then you draw the Bode magnitude plot, which means you need to calculate capital M. It's the following. So M is 20 log 10 magnitude of T of j omega. So this is 20 log 10, all of that stuff. The great thing about the Bode plots is you're plotting it in a log scale, which means that if I have divisions, if I have multiplications, they become additions and subtractions. So here is the beauty. This problem has numerator dynamics, right? There is stuff going on here, funny stuff here. But what we did not do was we did not go back to the frequency response function. We did not do the derivation and set. I write it in terms of the frequency ratio. We did not do any of those differentiations. We did not find out where the peak frequency is. We could do that, including all the effects of the numerator dynamics. But the beauty of the Bode plot is it is essentially taking this very complicated system and splitting it into multiple parts. It is going to handle the numerator separately. It is going to handle the denominator separately. And then you're going to combine everything together. Okay? Which is by using superposition, essentially what the log scale is trying to do. So we don't need to keep doing the differentiation every time if you have numerator dynamics, is what my point I want to convey is. Okay? And you'll see that in the next problem. So here I have M. First term is C, so 20 times log 10 of C. C is at 1 by 10. Okay, so I'll just write it as 1 by 10 if you don't mind. It's a nice number. Then I'm going to have 20 times log to the base 10 of 1 plus something square whole to the power 1 by 2. That square root, I'm going to bring it out. So that's going to become 10 log 10 likewise, all the square roots I'm going to get rid of so that it all becomes a factor of 10 instead of 20. So then I have 10 log 10, 1 plus omega square, omega p 1 square. And then lastly, minus 10 log 10 all of us on the same page? How did the factor of 20 go? Yes, sir, question.
The only part that I was a little bit confused about was how you got the transfer function for the Bode plot in that form was a w squared over 10 squared, the one to the left. Yeah, in that form. Yeah.
Oh, we just did that here. All of these steps. You write that first in the standard form there. And then I have a j omega here. And then I have to take the magnitude of each of these numbers. Okay? This is the procedure you follow for any real distinct situation, any real repeated situation. Okay? This is a very general procedure. Now what I'm going to do is I'm going to say that this total M is split into multiple parts. So I'm going to say this is M1, M2, M3, M4, so that capital M is M1 plus M2 plus M3 plus M4. And all I have to do is I have to perform asymptotic analysis 4 times, which is fairly straightforward in this problem, because what you have done now is you've taken a second order system and you have split it into multiple first order pieces. Essentially each of them are a first order piece, which we already know the behavior of. Any questions so far? First piece, M1, right? Log 10 of 1 by 10, 1 by 10 is 0.1, log 10 of 0.1 is minus 1, so this is just minus 20 decibels. This is a straight line. On the M versus omega plot. Do the same thing for the second one. So M2 is plus 10 log 10 omega z1 is 1 radian per second. Okay? Asymptotic analysis for very small values of omega less than 1, large values of omega much greater than 1. Okay, so omega much less than 1, I get M2 low. This is a low frequency asymptote. Is approximately log 10 of 1, because omega square by omega z1 square is a very, very small number. Okay? So I can ignore that in terms of 1, and so this is 0 decibels. Likewise, for very large values of omega, this is now going to give me the high frequency asymptote. So this is M2 high. Omega square by omega z square is much larger compared to 1, so this is 10 log 10 of omega square by omega z1 square. Get rid of the square, so this becomes 20 log 10 of omega by omega z1. So these are essentially your cutoff frequencies or corner frequencies. You have multiple of them in this particular problem. So this becomes a high frequency asymptote, and obviously they meet when omega is equal to omega z1. M2 low is equal to M2 high is 0. And then just for this particular case, what I will consider is I will consider a decade increase in omega versus omega z1. Okay, so let's say that omega is 10 times. M2 high is 20. Which just gives me 20 decibels. Another decade. And you obviously see that M2 high is going to give you 40 decibels. Okay, so M2 high, 20, 100. omega z1 divided by omega z1. So this gives you 2. So 2 times 20 is 40 decibels. You get the story. It's going to keep increasing. So if you have a 0, it's going to keep increasing at a rate of 20 decibels per decade from its cutoff frequency. So for a 0 of the system, if you have numerator dynamics, then increases by 20 decibels per decade after its cutoff frequency. I want to see if there are any questions so far. First term taken care of, second term is a 0. So if you have a 0 in the system, no questions asked. The low frequency asymptote is going to be 0 decibels. The high frequency asymptote meets the low frequency at the cutoff for that 0, and then it keeps increasing by 20 decibels per day. Okay, and the same story goes for the poles. We have already done this in the past. I'm just going to refresh your memory here. So I take the next term M3, but please notice when I say M3, it is inclusive of the negative term. It's not just a plus 2. So M3 minus 10 log 10 omega square omega P1 square omega P1 is 10 radians per second. You perform the same asymptotic analysis, low frequency, high frequency, they meet at the corner frequency. What's the corner frequency here? It's omega P1, which is 10 radians per second. Okay, so let's do this. For omega much less than omega P1, okay, I'm taking the term M3. This is going to give me M3 low. Omega square by omega P1 square is much smaller compared to 1, so you can neglect that term. So this is approximately minus 10 log 10 of 1, which is 0 decibels. Exactly the same story for the omega greater than omega P1 case. The square becomes much larger than 1, so I end up getting M3 high is minus 10 log 10 omega square by omega P1 square. Get rid of the square, bring it out, so that's minus 20 log of omega by omega P1, the base 10. Please do not forget the factor of minus 20. We've done this in the past, so if you have a pole, real and distinct of course, you will see that the high frequency asymptote is now going to reduce at 20 decibels for every day, right? So M3 high decreases by 20 decibels per decade after omega P. Last chance for questions. Is this clear to everybody? It could be boring, mundane, and all these things, but I still have to do it. I'm going to do it step by step. Okay? You've got to do the same thing for M4. I'm going to wave my hands on that because this is another pole. It's a real distinct pole. Its behavior is exactly the same as this. Right after I go from omega P2, which is 100 radians per second, I decrease by 20 decibels. Okay? So I'm going to summarize this behavior by writing everything down. So in summary, M1 is minus 20 decibels, nothing done there. M2, low, 0 decibels. M2 high was 20 log, whatever that thing was. Was 20 log 10. Omega by omega z1. This is the behavior of the zeros. Okay, so if you have a 0, you're going to see it increasing by 20 decibels per decade. Then the third thing, M3 low, 0 decibels, as we just did here. M3 high is minus 20 log 10 omega by omega P1. This is a decrease by 20 decibels per decade. This is increase. And the last one, I'm not going to do it, but the behavior is the same. So M4 low, 0 decibels, M4 high, minus 20, decrease by 20 decibels per decade after omega P1 and omega P2 respectively. Two ways to solve the rest of the problem. Okay, one is the laborious donkey work way, which I'm going to do. And that method never fails because it's stubborn, right? I tabulate everything. Okay? So I say omega. Then I write each one of them, M1, M2, M3, M4, and M, which is the sum of all of this. I start with some random value of omega, 0.01. Okay, all of them are in radians per second. And then 0.1, 1, 10, 100, 1000. When I say 1, it's omega Z1. Omega P1. Omega P2. People in the back, can you see my writing clearly? And then you tabulate each one of them. Okay? M1 is always minus 20, so I don't need to do any tabulation. So this is minus 20, minus 20, minus 20, minus 20, minus 20. Okay, this is a stupid way of doing things, but this always works. M2, the low frequency asymptote is always 0 until I hit omega Z1, so I put zeros all the way from 0.01 to omega Z1. Okay, so I have 0, 0. I come to omega Z1, look at M2. The high frequency and the low frequency become the same. Then I start increasing by 20 decibels every day. Okay, so plus 20, 40, 60. You can increase the number of values of omega as well. You can go to 10 to the power 4, it's completely fine. Do the same thing for M3. It's 0 all the way until you hit the first corner frequency for that pole, which is M omega P1. So that's 0, 0, 0, 0, minus 20, minus 40, because I'm increasing by 20 decibels, decreasing by 20 decibels per decade. Okay? Same story for M4. All the way from 0.01 to 100, the low frequency asymptote, 0, 0, 0, 0, 0. Then I increase by, or decrease by minus 20, decrease by 20, or increase by minus 20, whatever you want to call it. I don't have room for one more entry, but you get the idea. And then what do? You add them all up. Okay? So this is going to give me minus 20. Then minus 20, 0, 0, and 0 is still minus 20. Minus 20, 0, 0, 0 is still minus 20. Suddenly things start lighting up. Minus 20, plus 20, plummet down positively to 0. Minus 20, 40, and minus 20. What's that adding up to? 0. Minus 20, 60, minus 40, minus 20 adds up to minus 20. Etc. Plot it. M is in decibels, and I have omega in radians per second. This is 0, minus 20, minus 40, minus 60, and so on and so forth. Okay. Then I have 0.01, 0.1, 1, 10, 100, 1000, and so on. Draw lines at the corner frequencies. Excuse me. It's a fine taste of chalk dust. All right. So from 0.01 all the way up to, I believe, 1, I'm at minus 20. So just a straight line. Okay? Then from 1 to 10, you see that I have to increase by 20 decibels per decade, because this is the effect of the 0 coming into play. Okay, so I go from minus 20 to 0 all the way here. This is 20 decibels, 1 decade, and then from 10 to 100, I'm sitting on 0, so it's just a flat line. And then all the way, if you continue this charade, you will find out that this is going to decrease at a rate of 20 decibels per decade. And so this total line is your total M. Okay, and you can also do the following. I'm not going to do it, I'm going to show it in my lecture notes. You can plot the individual pieces, M1, M2, M3, M4, and then add them up on the plot itself, instead of writing out these numbers. I like this because I can see the numbers visually. This is better for me, but you do your own thing. The actual plot is going to be a smooth plot, not these kinds of broken chunks. But this is the asymptotic analysis, so that's why it looks broken up. This is a nice problem because it has nice numbers. Don't expect the same charity in the final exam. But you get the idea, you get the basic idea that if you have numerator dynamics, it does not matter. I can still use the information I have from before and plot what I can. I have a few more minutes for starting another problem. I want to see if there are any questions on this one. And while I'm at it, please go to recitation if you can. They're going to solve a couple of problems. On Wednesday, I'm going to take a circuit problem from scratch, obtain the system equations, and then plot the Bode curve. Okay? All right, next one. I'm going to go with the simple one. I'm going to take an underdamped system. Oh yes, question.
The increase and decrease by 20, is that true in any situation or just in this particular
Oh,
problem?
any situation. So if you have real distinct roots or real distinct poles or real distinct zeros. If you have real and distinct zeros, this is always true. If you have real distinct poles, always true. Any other questions, please, before I go ahead to the next one? Yes, this is a very general problem. I mean, even though you have some numbers, this is still very general, okay? Constant lines remain constant. If I have zeros that are real and distinct, increase after the corner frequency for that zero, which is the zero of the system. And same idea for the poles, but it's a decrease, okay? So underdamped system. I'm going to consider a very simple case. Okay, so let's say here is a transfer function. You always want to write the transfer function in the standard form. Okay, so some constant before the Bode plot. The standard form of the transfer function, if you have an underdamped system, which is for zeta less than 1 and greater than 0, obviously, because you have a stable system. This is C times whatever numerator dynamics you have, does not really matter. The denominator, S square omega n square plus 1. Okay, so you can have maybe this is the standard form. I will do the special case today. Okay, the special case is this nice simple thing. Right, the constant is 1. I don't have any numerator dynamics. This is similar to the problems, the first problem of your homework. How to draw the Bode plots. Very simple. First write the frequency response function. P of j omega. 1. S square, so I have a j omega whole square, so that's minus omega square, so that's 1 minus omega square omega n square This is a frequency response function. Magnitude of this function is going to be 1 minus omega square omega n square whole square, the square root of the sum of the squares of the real part and the imaginary part. Do not square the j, please. Whole square, whole to the power 1. Bode magnitude plot. Calculate m. So m 20 log 10 of t of j omega. So 20 log 10 of all those creatures there. So this is 20 log 10, 1. All of that. So that's just 20 log 10 of the numerator minus 20 log 10 of the denominator. So capital M 20 log 10 of 1, which is a numerator, which is obviously 0, minus, I have a square root, I have the 20, the factor of 20 becomes 10. So this is minus 10 log 10 obviously this is 0. So m is minus 10 log 10 exactly the same approach as before. Okay, there is nothing special here too. Asymptotic analysis. Here your corner frequency, if you have the underdamped system, is going to be your natural frequency. Okay, so that's where the special action takes place, resonance and all these kinds of things. So for omega, you see what happens? If omega is very small compared to omega n, then what you see is this term here vanishes. This term here is also very small and it vanishes. So I'm going to have minus 10 log of 1. Which is just 0 decibel, so this is good. Okay, 2 more minutes. For very large values of omega n, this omega, not square, I'm sorry, just omega n. This now gives me the high frequency asymptote. Watch this. It's going to be omega square by omega n square, much larger than 1, so the 1 can be discarded. So that's minus n log 10 of omega square, omega n square whole square. But if I look at the first term and if I get rid of all the squares, it becomes a 4th power. So I'm going to have omega by omega n to the power 4, which is obviously going to be much larger than the square term here. So I can neglect this guy. And so I have m high is minus 10 log 10 omega square, omega n square whole square, or minus 40 log 10 of omega by omega n. And so this obviously means, yes, question. Quick question.
Where did the minus sign go for the omega squared over omega n?
Oh, which one?
When you were doing m high, the first.
Oh, you can put a negative sign, but I'm squaring a negative number. Becomes positive. Okay? So here is what happens. If you have an underdamped system, in this special case, I'm going to have a low frequency asymptote of 0 decibels. This is a high frequency. Please go to recitation. They're going to pick up on this, and I'm going to solve a problem on Wednesday.